Good morning.
Good morning, sir.
Good morning, sir.
Yeah.
Good morning, sir.
Okay. So today we have around 19 students on board. Let's continue. So yesterday we were talking about the enzymes. So we have discussed the concepts about the enzymes with respect to their characteristics, with respect to their catalytic power, then the specificity. Then you have the catalysis. There are different modes of catalysis, what you can think of, that how the interaction it takes place between the enzyme and the substrate. So there it was the lock and key model which we know, but then lock and key model, it had some disadvantages, because it says that it is having an complementary site to that of the substrate. But then even though if it is the complementary, you may require an higher amount of energy to overcome the energy of activation. So it was the induced fit mechanism, or the hypothesis which was accepted, which tells us that the active site of the enzyme, it has a complementary site to that of the transition state of the enzyme substrate complex. Fine. So whereby the all the possible non-covalent bonds are taking place, and you have that complex which is formed, that is called as the enzyme substrate complex. Fine. So this relates to the uh, specificity of the enzymes for the substrate, and also it gives us an idea that the rate of the reaction may be increased, because you are forming a complex which is a transition state, which is an unstable state. So in that unstable state, it is the energy of activation which has been lowered down, and it may result into the uh, increase into the rate of reaction. Fine. So that is what we have seen. Then in case of the catalysis, that how does the catalysis might be taking place? So we have seen the three different modes which could be possible for any one of the enzyme. If you take the first one, could be your general acid base catalysis, whereby simply the behavior of the water which is present into the environment, or some of the residues, okay, some of the functional group of the residues which could be involved into the donation of proton or the acceptance of protons, right? So that could be your general acid base catalysis. Then the second what we saw was the covalent catalysis, whereby the enzyme, it first break the bond between the substrate, okay, and it may get bound to one of the molecule of the substrate, while the second molecule is released, and in the second step you can say that the bond which is formed between the enzyme and the substrate, that is being broken, and you get the substrate which is converted into the product. Right. And the third one, obviously it is with the help of some cofactor or a prosthetic group. So specifically it is the cofactor, that is the inorganic ions which plays a role here. The possibility could be that the charges which are present into the active site of the enzyme and the charges which are present onto the substrate could be similar. Okay, and in this case, if the reaction has to occur, these two entities, they should come closer to each other, and for that we require some cofactor which is positively charged, so which can get bound to both the negative charges of the active site as well as the substrate, so that a complex could be formed and the reaction can take place. Right. So these are the three possible modes for understanding the catalysis of the enzymes. Fine. But the most important thing about the enzymes is that you should be able to understand that what is the rate of reaction of that enzyme. And for that, a new stream which came up, that is called as the enzyme kinetics. So scientists, they spend uh, their time in understanding that how do you determine the rate of the particular reaction or the velocity of the reaction. Right. So it was the efforts of many scientists, but it was Michaelis and Menten who came up with a what you can say, some hypothesis where they could put some mathematical statement or a mathematical formula which will give us the relationship between the enzyme concentration, the substrate concentration, and the concepts such as the Km or the maximum velocity. So it gives a mathematical correlationship between all these terms, so that the rate of the reaction or the velocity of the reaction can be calculated, right? So as I told you yesterday, that it was based on some three hypotheses. Okay. I'll present the screen and try to explain that what were those hypotheses, how this equation was derived, what are the significances of this what we can say, the equation, and how it has really helped in calculating the rate of reaction. So I think already Nupur has explained that, but still we'll try to see some of the glimpses of that particular equation. So is the screen visible?
Yes, sir.
Yeah, okay. So this is the graph which I told you, that it was the substrate concentration, one of the important parameter which has helped us to understand this behavior of the enzyme. Okay, so that the rate constant or the velocity of that particular enzyme can be determined, right? So this graph I told you could be compared with the bacterial growth curve. So as we have divided the bacterial growth curve in three stages, the same way you can divide this enzyme substrate experiment into three stages. Okay, so here also you can see that there was a linear increase in the initial stage, okay, which indicates that the reaction is occurring constantly with a constant increase. But then as you go on increasing the substrate concentration, the velocity is not up to the mark, that it is not going on increase, going on increasing in a doubling form. Okay, so you can see some steep into the slope into the graph, but at higher concentrations, if you go in the further direction, you see that the velocity is not increasing, it remains constant. So you are getting a plateau region, okay, which is similar to that of the stationary phase of your uh, bacterial growth curve, right? So that indicates that the enzyme is saturated, or we have reached to an stage that is called as the maximum velocity, right? Let's take this equation which is shown here, that you are simply general equation what you are taking, that you have the enzyme, to that you have added a substrate, and this enzyme plus substrate is converted into enzyme plus product. Now this reaction, it can be splitted in two individual reactions, whereby you can see here that E plus S is giving you the ES. Okay. Now further this ES will be then converted into E plus P. Okay. So here we are not considering the possibility of an intermediate called as EP. So we are skipping that particular step here. So we are simply dividing into these two half reactions. Now each of this reaction, when it is occurring, it will have its own rate constant. Okay, the equilibrium constant, I think all of you know what is that equilibrium constant. So this equilibrium constant is denoted by K. So when the forward reaction in this, that is E plus S, is converted into ES, it will have a rate constant that is K1. Now the possibility of this ES to go back into the E plus S is also equal. So when it is going back from ES to E plus S, it will have a rate constant that is K minus 1. K minus 1 rate constant is never negative. It is simply to indicate that it is going into the reverse direction. Laksha diya. Then you have this ES, which is converted into E plus P. Now when this reaction is taking place, it will have a rate constant that is K2. Okay, and here again we are considering a possibility where this product can again be converted back to the substrate, where the E plus P can again be converted into ES. So it will have a rate constant that is K minus 2. Right. So you have the four rate constants for this what you can say, imaginary reaction what we are trying to understand, that is E plus S is converted into E plus P. And we want to derive this equation, the equation which was given by Michaelis-Menten, that is velocity. V0 is the initial velocity or the velocity of the enzyme, which is equal to the maximum velocity into substrate concentration upon Km plus substrate concentration. Fine. So here you can see that it is giving us an mathematical relationship between the velocity, the maximum velocity, the substrate concentration, and the rate constant. Sorry, not the rate constant, but the Km. Now Km is a term which relates to the affinity of the enzyme toward the substrate. So we maybe will talk about this at a later stage, but you have this equation which we want to derive. Now before I go to explain the different hypotheses, here we should understand that what are the different forms of the enzyme which you may come across. Okay, so initially you are adding the free enzyme. So you may have the enzyme which could be in the form of the free enzyme or the unbound enzyme. Okay, you have the second form of the enzyme where it could be into a complex, that is ES complex, that is the bound enzyme. Okay, that is the enzyme has bound to the substrate. Okay, and then the further reaction could be. So you have the enzyme in the two forms, that is unbound enzyme and the bound enzyme. Now throughout this graph, if you look at it, you may see that the enzyme could be in the different forms. Like in the initial stages, where if you compare it, you have the enzyme concentration which is higher as compared to that of the concentration of the substrate, because you are working at the lower concentrations. Okay, so initially there is what? There is a higher amount of enzyme concentration as compared to that substrate concentration. So at this particular stage, you can imagine that the reaction is occurring very fast because the enzyme is much more as compared to that of the substrate concentration. Right? So you may have the reaction which is easily taking place. You can imagine that it is into a doubling form, so you may get a straight line. So this is what you can see here, that you are getting a straight line and steady increase into the velocity or the rate of reaction which can be seen. But as you go on increasing the substrate concentration, what is happening? You may come across a stage where the enzyme concentration and the substrate concentration is equal. Fine. So if you move further, what you see that there was an change into the nature of the graph, that you are getting a bending in at this particular stage. So this stage is occurring at the higher concentration, which is indicating that the enzyme is getting occupied by the substrate, because here the substrate concentration is going to increase as compared to that of the enzyme. Okay, and that has related to the decrease into the velocity. Okay, so you are not having the exact doubling. That is what I mean to say here. And you may come to a plateau region where you say that all the enzyme which is present into your experiment, all that enzyme is into the bound form. Okay, means you are reached to a stage whereby the enzyme is being saturated. Okay, and that stage is nothing but the maximum velocity. Right. So throughout this graph, you may find the variation into the behavior uh, the behavior of the enzyme, because this enzyme is being affected by the variation into the substrate concentration. Right. So keep this particular point into your mind. Now I'll go into the next slide where we'll try to derive this particular equation. Okay, and we'll try to understand the different assumptions. Yeah, so the same equation I have put it into a straight line. Now we are talking about the velocity. So here scientists thought, why not go for the initial velocity? Now how do you calculate this initial velocity? So this initial velocity is calculated at the starting point of your reaction. Means the moment you add the enzyme and the substrate into the test tube or any type of instrument, okay, so that the reaction can occur immediately, that is maybe within 30 seconds or 60 seconds, you stop the reaction. Okay, so if you want to find out the initial velocity, it is very much essential that you stop the reaction at the early stage of your experiment. Right, so maybe within 30 or 60 seconds you can stop the reaction and try to find out the velocity. So under that condition, the possibility of formation of ES is very less. Okay, then conversion of that ES into the product is also very less. So the conversion back of this product back to the substrate is very less. So it's negligible. So maybe at this particular stage, we may skip upon this rate constant, that is K minus 2. So we are talking only about these three rate constants, right? So in this particular reaction, which we have divided into two reactions, that is E plus S, which is converted into ES, and then ES, which is then converted into E plus P. Now, if I want to find out the rate constant for this reaction, so one thing which we have already seen, that the rate constant or the rate of that particular reaction is depending on to the what you can say, the reaction, which is a very slower reaction. Okay, so the slower reaction into a given reactions or in a metabolic pathway is the one which is the rate limiting step of that particular pathway. Right, now here in this case we have two reactions, that is E plus S is converted into ES. Now here the possibility of enzyme and substrate reacting with each other could be fast, so you are getting this enzyme substrate complex. But now here it is the concentration of the enzyme substrate complex is going to decide whether the reaction will go into the forward direction or into the backward direction. Fine. So here the splitting of the ES is going to decide whether the reaction will be into the forward direction or into the backward direction. So yeah, you should what you can say, this rate of the reaction is going to depend upon what? The enzyme concentration of the enzyme substrate complex. Fine. So we got this particular factor, but then whether it is dependent upon K1 or K2. See, if when you are going looking for an completion of the reaction, obviously what the concept says that the ES should be converted into E plus P. Fine. So it is the breakdown of the ES which is important. So this reaction, that is ES, conversion of ES to the E plus P, okay, is the slower reaction. Okay, and this reaction is actually deciding the rate of the overall reaction. Fine. So the K2 is the one which is deciding the rate of this reaction. So the velocity can be put in this equation, that V0 is equal to K2 into enzyme substrate concentration. Okay, so the velocity of this reaction is dependent upon K2, and obviously it will depend upon the concentration of the ES. Okay, so this is the first equation what we have got here. Fine. So just keep this in mind. We'll come back to this equation because we'll require it for the further rearrangements. Okay. Then so this state what we have studied could be called as a pre-steady state. याला काय म्हटलं जातं pre-steady state, because you are working at the initial velocity. Now as the reaction proceeds, that as you are going on increasing the substrate concentration, as the reaction is proceeding, you come to a stage, okay, and that stage is called as a steady state. So it was in 1925 where Briggs and Haldane, they have proposed this assumption of the steady state assumption, that is called as the steady state assumption. Now this steady state assumption, it tells us or it gives us an idea about the behavior of the enzyme substrate complex. Okay, so this what they wanted to say, that this enzyme substrate complex can be converted into the product, that is enzyme plus product can be formed, or this enzyme substrate complex would be converted back into the enzyme or the substrate. Right. So when you're talking about a steady state assumption, where we say that the enzyme and substrate, they are at the equilibrium. Okay, so they are at the same concentration. So at this particular stage, the possibility of the formation of the enzyme substrate complex is equal to the breakdown of the enzyme substrate complex. Okay, so you have the equilibrium between the rate of formation of the ES as well as rate of breakdown of the ES. Okay, now when you are talking about steady state, what we can say, that this rate of breakdown is equal to rate of formation, right? So for that we should have some equation whereby you can determine the rate of formation of the enzyme substrate complex, and you should have an equation which will give you the idea about the rate of breakdown of the enzyme substrate complex. So this both these equations can be put in this way, that rate of ES formation, okay, so it will be dependent upon what, K1. Okay, because the rate constant is K1, so K1 is equal to, it will depend upon the concentration of the enzyme and the concentration of the substrate, right? Now here instead of putting it concentration of the enzyme, we have put it into this form, that is ET minus ES. Okay, because you cannot determine the free enzyme, the concentration of the free enzyme, so it can be determined by this equation, that is ET means the total enzyme and ES means the enzyme substrate complex. So ET minus ES, so by this particular term you can calculate the concentration of the free enzyme into the concentration of the substrate. So this is the equation for rate of ES formation. Now next, rate of ES breakdown. Okay, so here the breakdown of the ES, as I told you, that it could be either into the forward direction or it could be into the backward direction. So for this rate of breakdown, it depends upon these two rate constant, that is K2 and K minus 1. So you have to consider both these ways, so which can be put here like this, that rate of ES breakdown is equal to K minus 1 into, obviously it will depend upon the concentration of ES, okay, plus, because it is dependent on both these factors, so we have added it, so plus K2 into ES, right? So these are the two equations which gives us the idea about the rate of formation and the rate of breakdown. Now we are talking about what, the steady state. The steady state, what does it tell us? That this rate of ES formation is equal to rate of ES breakdown, right? So this equation is equal to this equation. So simply you put a this in front of each other, so one becomes the right side, the other becomes the left side. So I have simply put it like this. Now we start rearranging. Okay, so these are simple mathematical or the statistical steps which has been taken into consideration. So in this right side, you can see that from this right side, we'll multiply this substrate concentration to each of these term, while in this side, toward the left side, you have this ES which is constant. So we'll remove the common factors and we'll try to bring these constants in one particular bracket. So if I do the rearrangement, I get this equation. So what I have in this right side, what I have done, I have multiplied this ETES by the substrate concentration. So you get this particular thing, and here I have brought down the ES as a common. So the constants are taken into one particular bracket. Further, what has been done? What I did, I shifted this minus K1, sorry, this K1 ES into S. So this I have shifted it onto the right side, right? So again, when I bring it to the right side, I have this ES which is common, right? So again, I have removed the ES which is common, and I got this equation, that is K1S plus K minus 1 and K2. So all these constants are in one particular bracket, and ES is the constant, right? So this is the rearrangement. I think all of you might have done it as an assignment, which I have told you that you have to write it down in your notebook. So you try to do these rearrangements and you will able to understand. Further, you can see here that yeah, then I have solved this equation for ES. Okay, so if you solve it for ES, you get this right hand side divided by the left hand side, right? Then again we have made some rearrangements where all these constants, they are brought back in one particular bracket, right? So here I think so it is simply divide the numerator and denominator by k1. So if you divide it by k1, so this k1 it gets cancelled, this k1 it gets cancelled, and this k2 plus k minus 1 it becomes divided by k1. So by doing this, what we have done, we have brought all the constant, that is k1, k2 and k minus 1 on at one particular site. Okay, so these constants which we have gathered together, these constants are nothing but the Michaelis-Menten constant. Okay, so it can be denoted as km. Okay, although I have not put it here as a separate, but you can call all these constant as, instead of having these three constant, we simply call it as what, km. So km is all the three constants which are playing an important role for the reaction to occur, right? So we get this equation where we have now calculated the value of this enzyme substrate complex as this particular formula. Now further, yeah, we have modified it. So instead of having all these constant, we have put it as what, km. Now we'll substitute this value of es into the first equation which I told you. So the first equation, what, v0 is equal to k2 into es. So we'll what you can say, uh, instead of this es concentration, we'll put this particular formula. So by doing that, I get this equation. So v0 is equal to what, k2 into et into s upon km plus substrate concentration. Okay, so we got this equation. So this is what, after the steady state assumption, we have come to this equation. Now we'll move to the third assumption, and that third assumption, it tells us about the maximum velocity. Now when you're talking about the maximum velocity, where there you have that your enzyme substrate complex is formed at the maximum number. Okay, where you can say that all of your enzyme, okay, all of your enzyme is in the form of what, es, that is the enzyme substrate complex, that is your enzyme is saturated. So the maximum velocity is a state where you have your total enzyme into the enzyme substrate complex, fine. So this particular term, that is k2 into et, can be called as what, the Vmax, that is the maximum velocity. Now here we have considered the total enzyme is in the form of what, the enzyme substrate complex. So you can see here I have shown this particular equation, that is es is equal to et Vmax, that is equal to, that is the Vmax. Okay, so under the condition of maximum velocity, your total enzyme, okay, is in the form of what, enzyme substrate complex. Okay, so Vmax, if you want to define, Vmax could be what, k2 into enzyme substrate complex. Okay, now here enzyme substrate complex is equal to the et, that is the total enzyme. So that is why we have converted this k2 into et in the form of Vmax. Okay, and this is what is the equation what you get, that is v0 is equal to Vmax upon Vmax into substrate concentration divided by km plus substrate concentration, right? So this is the equation what we have derived, and this equation is called as what, the Michaelis-Menten equation. Okay, and this equation, as I told you, that it gives us the relationship between the initial velocity, the maximum velocity, and the substrate concentration, right? So I think it is clear that how this equation was derived. So you have to consider those three assumptions. The first one can be called as the pre-steady state assumption, that is the initial velocity. Then you have the steady state assumption, where rate of breakdown of the es is equal to rate of formation of the es. Okay, and the third assumption is what, that the maximum velocity, right? Where under this maximum velocity condition, you have the total enzyme which is into the form of the es. Okay, so it relates to what, the saturated enzyme. Okay, so Vmax is what, it is the maximum velocity where your total enzyme is saturated. Okay, now remaining is what, km. So km is what, it's a rate constant, it's a constant, but this constant can be calculated and it can be related in the, or it can be expressed as what, the substrate concentration, right? So there is a condition which can be put here, that half of the maximum. Okay, so the rate at half of the maximum, the concentration at which you have the half of the maximum velocity is nothing but the km. Okay, so I think in her presentation, Nupur has given that particular condition. So you can see here that km is equal to substrate concentration when V0 is half of the maximum velocity, right? So we can put those values here, and you can see here that km is equal to the substrate concentration, right? So that was about all about the maximum velocity. Sorry, the Michaelis-Menten equation. So in addition to this, she has also brought about the different terms that k cat and etc etc. So kindly read it out, try to understand, and if you have any difficulty into that, we'll surely talk about it afterwards, right? So that is all from my side. So I think it is clear about that particular equation what she has presented. So keep those three assumptions, and you should be aware of these three assumptions. Fine. Yeah, Nupur, I
Yes,
think
sir.
I have conveyed the point what you were trying to explain. Now we'll come back to your presentation.
Okay, sir.
Yeah. So you can present your screen. Wait, let me.
Is the screen visible, sir?
Yes, yes, yes.
And am I audible?
Your
Clearly?
voice is breaking.
Uh, just wait a minute, sir.
Okay. Meanwhile, she adjusts
Now,
herself. Yeah.
am I audible, sir? Now?
Yes, you are audible. But before you proceed, I just wanted to ask a question to all of you that she is now explaining us about the transformations of the Michaelis-Menten equation. Okay, that is the double reciprocal plot. So why there was a need which was felt that you should go for the transformation into the MM equation? Can anyone tell me why do you require these transformations or the modifications into the MM equation? Yes, who can tell? See, if you want to calculate the velocity, you should know the values of this Vmax, that is the maximum velocity, the Km, etc., etc. Yeah. So why there was a need which was felt that you should go for modifications of this MM equation? Can anyone tell? Come on, be fast. Sonam, Patkan, Priyanka. Okay, Nupur, can you tell?
So, whatever the graph we have seen before, like that rectangular hyperbolic graph,
Hmm.
the value of Vmax can be approximated from that graph. That was the basic graph which they have plotted. But with double reciprocal plot, we get more accurate values of Vmax and Km.
But why
That's
is
why
that
the
in the rectangular hyperbola you cannot get the exact values?
uh,
Do you have the graph in your presentation?
rectangular hyperbolic graph.
Yeah, yeah, yeah.
Uh, yes, I have it.
Can you show it?
Yes. Here is it, sir.
Hmm.
Can you?
Yes, yes, I can see it. I think all of you can see it. Now, if you look at the graph, what does it show you? That the maximum velocity line is shown, that is the dotted line is shown somewhat above that of the plateau region. See, in this case, theoretically, when you are talking about, you can get an exact plateau where you cannot show an increase into the velocity, but practically it will never happen. See, it's an enzyme which is getting saturated at the maximum velocity, but is it that the enzyme is going to inhibited? No, the reaction is going to occur. It is going to degrade that substrate into the product. It will take a new substrate. Again, the reaction is going on continuously. Fine. So here in this case, what could happen, that instead of getting your plateau, you're getting a zigzag manner at that particular position. Although I cannot show here, but just 1 minute. I'll try to show it with the whiteboard. I'm creating the whiteboard. Yeah. Suppose this is the x-axis and the y-axis, and this is what you got as an graph. This is the plot which has got. Theoretically, if I say yes, that this graph is correct, okay, just 1 minute. But then practically, when you're doing the experiment, you may not get a plateau like this. So at this particular stage, you may get something like this. There could be an increase and decrease, etc., etc. So if you have such kind of zigzag manner, you cannot calculate the exact value of the uh, Vmax, or the accurate value of the maximum velocity. And if you cannot calculate the Vmax, obviously you cannot calculate the Km, because the value of Km can be calculated only from the value of Vmax. So because it is half of that Vmax. Okay. So this plot which was given at that particular point, they found this difficulty where you are not getting an accurate value. So for that, what they thought, why not convert this equation or this graph into a form where you are getting a straight line which is passing through the origin, means as that of the standard graph what we draw during the qualitative estimation. Fine. So why not get a straight line graph? Okay, so that you get the accurate value of the maximum velocity, and then you can calculate the Km. Fine. And for that particular purpose, they have gone for the modification. Now let's see what kind of modification has been done into the plot. Yeah, now you can present your screen.
Okay, sir.
Yeah.
Is the screen visible, sir?
Yeah, it's visible.
Yeah. Uh, so as we have rephrased the entire equation, it's V0 is equal to Vmax into substrate concentration divided by Km plus substrate concentrations. Now we'll see two transformations in this equation. They are simple ones. So first one is a Lineweaver-Burke equation. What the transformation, it's not a huge transformation. Actually, we are just going to witness what that simple mathematical operations, and we are going to derive one new equation. So the our equation can be algebraically transformed into equations that are more useful in plotting experimental data. So sir just said that practically it's not possible that that we can get accurate values of Vmax from the previous graph. So we are taking reciprocal of both sides. So the reciprocal, it will become like 1 upon V0 is equal to Km plus S divided by Vmax into S. So we'll separate the components of numerator on the right hand side of the equation. It will give us this equation, like 1 upon V0 is equal to Km divided by Vmax into S plus substrate concentration divided by Vmax into S. So it will further simplify into 1 upon V0 is equal to Km upon Vmax into S plus, so both the substrate concentrations will cancel at that point and we'll get 1 upon Vmax, that is the reciprocal of maximum velocity. So this form of our Michel's-Menten equation is known as Lineweaver-Burke equation. Uh, Now we'll see the double reciprocal graph that they have plotted here. We
Yeah,
can
just
see that.
I'll interrupt you. Just
Okay,
go back to the equation.
yeah,
Yeah. So simply what is being done here, there is a reciprocal which is taken. Means what we are doing, we are converting the typical Michaelis-Menten equation into a form that is y is equal to mx plus c. Okay, and this equation is for the straight line which is passing through the origin. Hello, Lakshat. So 1 upon v0 is what? Is y. Mx, that is km upon vmax is m, that is the slope. X is substrate concentration. 1 upon s. Further, it should be simplified like that. That is km upon vmax into 1 upon s. So km upon vmax is the slope. 1 upon s is the x axis plus 1 upon vmax is the constant. Mx plus c. So we will be converting this equation into the form that is y is equal to mx plus c, a equation for a straight line which is passing through the origin. Yeah, now you can continue.
yeah. So it so just said that in considering the y is equal to mx, the k upon v max and and an intercept of 1 upon v max on the y axis, that is 1 upon v0 axis, and an intercept of minus 1 upon km on the x-axis, that is 1 upon s-axis. So this plot, it has a great advantage of allowing a more accurate determination of Vmax because it is a straight line graph and which can only be approximated from simple plot of V0 versus substrate concentration graph. So this plot of enzyme reaction rates is very useful in distinguishing between certain types of enzymatic reaction mechanisms which we have seen before and analyzing enzyme inhibition. Actually, I have not gone into detail for enzyme inhibition, but the yeah, this is the graph they've plotted here. Uh, we can plot these double reciprocal plots for three types of famous enzyme inhibition mechanisms like uncompetitive, competitive, and non-competitive, that is mixed inhibition. And by the appearance of that this double reciprocal plot, we can analyze the which inhibition is inhibition is explained there. So it is that kind of useful. So we'll come to the slide a little later. Another transformation is Adie-Hofstee equation. It's given in Leninger in a very short form. What we'll do is we'll multiply this Lineweaver-Burke equation by Vmax on the both sides, and we'll after rearranging that Lineweaver-Burke equation, we'll get this Adie-Hofstee equation. Now, talking about Adie-Hofstee equation, it was actually in ancient times or the time when we were not having powerful computers or non-linear regression softwares for calculating the values of Vmax and Km. It was used because it is said that it was uh, rapidly giving the values of Vmax and Km. So it was that kind of useful, the Adie-Hofstee equation. Uh, so now we have seen or we have derived more specifically the equation we have derived is for only one substrate, and and the enzymatic reaction by having two two steps like enzyme plus substrate, and it were uh, combining and giving enzyme substrate complex and again transforming into free enzyme and a product. But it is not compulsory that the enzymatic reaction should be two-step reaction in order to obey the Michaelis-Menten kinetics. Most of the reactions are having more than two steps. Probably most probably the all the biological reactions. So in most of the enzymatic reactions, two or more different substrate molecules they bind to the enzyme, participate in the reaction. For example, if we have ATP plus glucose, they are going to convert into ADP and glucose 6 phosphate by the enzyme hexokinase. So these bisubstrate reactions, they are also determined by Michaelis-Menten approach. It's not compulsory that we should have only two-step reaction. Michaelis-Menten approach can be it I mean it can be done with this reaction which is having more than two steps also. So now we'll just come to this diagram, and I'll explain this by this diagram only. So enzyme. So in enzymatic reaction, if we are having two substrates, so the two substrates can come and bind to the enzyme in two or three different manners. Like you can see in first reaction, that is it it is involving a ternary complex. But when it is forming a ternary complex, like when this the enzyme, the substrate 1 is coming, the substrate 2 is also coming, so it's like a confusion, or that complex is forming because both are coming simultaneously, and enzyme is binding two substrate at a time, and it is converting into free enzyme and the two products of that particular substrates. But in ordered manner, first enzyme is coming, it is forming complex with an first substrate is coming, it is forming complex with an enzyme, and then second substrate is coming, it is forming complex with the previous complex, and then the conversion of substrate into products is taking place. Now in second type of reaction, there is no ternary complex, it is not forming, because you can you can see from this equation, like it is first enzyme is coming, it is forming complex, and the product is coming, and then that product is leaving that complex. Then second enzyme is coming, and that then second substrate is coming, and that substrate is that complex is converting into three enzyme and that particular product. So uh, the second case, the we can say that, which is more disciplined, where ternary complex is not forming, it is called as a ping pong or double displacement mechanism. I have given what I have explained is I have given in this slide, or I have that given in this slide. So you can see this graph. Yeah, I have taken this from Leninger. I have just what is what is done in this double reciprocal plots is the concentration of substrate 1 is changed while the concentration of substrate 2 is held constant, and it is repeated for several values of substrate 2. So by looking at this graph, they are kind of self-explanatory, that the in first graph the lines are intersecting, so uh, uh, we can easily predict that it must be involving the formation of ternary complex, because there is a lot of confusion is there, both substrates are coming simultaneously and the lines are intersecting. And in second graph, we can see the parallel lines. That is, first substrate is coming, and it is forming complex, and it is converting into product, and that product is leaving the complex. So parallel lines, it will indicate the ping pong or double displacement pathway which we have seen. So yeah, that was all about Michael's-Menten equation. So I have tried my best to explain explain the derivations and all the concepts related to Michael's-Menten equation. There are still one or two concepts that I have not understood. That those are in Leninger. So I have not included that in my presentation, but still I have given my best to explain it. So thank you so much for listening to this lengthy presentation, and thank you so much for your patience. Yeah, thanks a lot.
Okay, good. You can bring out those 2 points which you are not understood. Okay,
Yeah.
you can put it personal as a personal message, and maybe I'll cover it in the next lecture. Right. So before you stop your sharing, can you show me the LB plot?
Yes, sir.
Will take some 2-3 minutes more. See, what we have done, we have taken a reciprocal of the Michaelis-Menten equation, where I told you that we have converted it into the form that is y is equal to mx plus c. Okay, so then you have to put it in the form of a graph. So if you see here, what actually has been done, uh, yeah. So you can see that this is y-axis, this is x-axis, right? So on the x-axis you have the reciprocal of substrate concentration. On the y-axis you have the reciprocal of the velocity. That is the the velocity. Now, when you do this calculation, that is, you calculate the reciprocal of substrate concentration, reciprocal of velocity. If you look only at the positive graph, what you are talking, जो अपन normal graph काटतो तेवढा बघा तो. So in this case, what happens that all the points of your experiment, what you get, all of them they gather at this particular region, in this particular region. I think all of you can see the cursor. Cursor दिसतोय का मी मूव करतोय तो?
No, sir.
No, sir.
You cannot. Okay, because I don't have this particular. Let me see whether it is present in my graph or not. Mm, no, I don't have it. Just 1 minute. Yeah. You can stop your presentation, Nupur.
Okay,
I'll.
sir.
Yeah. Yeah. Can you see my screen?
Yes, sir.
Yeah.
Yes,
So in
sir.
this now you can understand. Yeah, this is the plot. What you can see here, that is the LB plot. Just look at this positive side. So you have the 1 upon s here. You have 1 upon v0 on the y-axis. So when you plot this graph, you see that all the points they gather in this particular region only. Okay, so if they gather in this region, you can draw a straight line, but the straight line it ends up here. Okay, so the point where this line is intercepting on the y-axis, that is on the velocity axis, that is the point which can be calculated as what? The Vmax. Okay, so Vmax is the point where this straight line is intercepting onto the y-axis. But now I want to calculate the Km. But Km is what? The substrate concentration. And I have plotted the substrate concentration on the x-axis. So what to do in this case? So for that reason, what they have done, they have extrapolated this graph onto the other side of the line. Okay, so you can see here that it on the other side of the graph, you can see that this extended region is there. So suppose here the values were 0, 1, 2, 3. This side it will be 0, -1, -2, -3, -4. Right? And then by doing that, they extrapolated, or they extrapolated this line which is intersecting onto the y-axis on the other side of the graph, and they had the line to a level where it will intercept the x-axis. So the point where this extrapolated line is intersecting onto the x-axis is called as the Km. Now all these values, that is of the Vmax as well as the Km, it will be in the reciprocal, that is 1 upon Vmax and 1 upon Km. So if you are asked that what is the Vmax and Km, you will have to convert this 1 upon Km into simple Km, or 1 upon Vmax into simple Vmax, and that is the value of your Km and Vmax. Okay. So here you are getting the accurate value of the Km and Vmax. But here actually you get it in the form of reciprocal, which you have to convert it into the simple form. The other thing, now as you are getting the value of Km onto the other side of the graph, it is represented as negative, that is minus 1 upon Km. Keep in mind that Km is never negative. It is simply indicating that the value what you have calculated, it has been from the other side of the graph where you have extrapolated the line, and that is why it is represented as what, minus 1 upon Km. Okay, so I think this LB plot is clear. Okay, so just keep in mind that the normal graph is not giving you the value of Km, it is giving only the value of the Vmax. Okay, so we have to extrapolate it onto the other side, and then you can calculate the Km value. Fine. So that is what I just wanted to tell here about the Km. And then in addition to this LB plot, and that is why it is also called as the double reciprocal plot, because you have the double graph. म्हणून त्याला double reciprocal plot म्हटलं जातं. Now in addition to this what you can say modification, that is the LB modification, you have two more modification. So one is what she has explained. So kindly refer that Leninger book. Okay, and if you have any problem into that, you just tell me, I will explain that particular graph also, but at a afterwards. I think it is clear up to this point. So put your roll numbers in the chat box. Avdut, write the numbers and send me across.
Okay, sir.
Yeah. Any questions? Already we have crossed the time, but still if you have any questions, you can put those questions or ask these questions tomorrow. So tomorrow who is going to present? I think the factors affecting enzyme activity.
Yes, sir. It will be
Okay,
Rajeshwari.
Rajeshwari. Yeah. So we'll see what Rajeshwari will tell us. Fine. So if he has finished with writing the numbers, roll numbers, we can call it for a day. Good day, all of you.
Good day, sir.
Thank you, sir.